I'm going to be focusing a little more on some of the detector features and caveats that we have been exploring and characterizing during commissioning. So the NIRISS instrument, NIRISS stands for the Near Infrared Imager and Slitless Spectrograph. It was built by CSA, the Canadian Space Agency. It's a single teledyne Hawaii 2RG Mercatel detector, and it can observe from 0.6 to 5 microns. On the right here is a single full frame image, which shows the 2.2 by 2.2 arc-minute field of view. This detector has 2048 by 2048 pixels, of which 2040 are light sensitive, and we'll talk a little bit more about that later. Plate scale is listed here. One thing I did want to highlight is that in the corner of every slide, I have links to documentation which expand on the contents of every slide, which typically goes to JDocs. Okay, so here on the left is just a schematic of the NIRISS optical path, which you can see here in the middle is this filter and pupil wheel section, which is expanded upon here. NIRISS has 2 wheels, which include a suite of filters, prisms that are available for the different science modes. And then on the right here is an illustration of the detector and the readout channels. So the NIRISS instrument has 4 parallel readout channels, which are listed here, and each of them have their own amplifier. You can also see the subarrays, the most common subarrays that are used for NIRISS, including the substrip 256 and 96 subarrays. Those are used for our sauce mode. And then the sub 80 subarray, which is used for the AMI mode. Okay, so what are the NIRISS observing modes? NIRISS has 4 observing modes. The first we'll talk about is the wide-field slitless spectroscopy. This is identical to the mode that NIRCam uses, but slightly different filter complement. When you use the wide-field slitless mode, you typically observed using a series of direct images and then inserting 2 orthogonal grisms into the light path, which disperse the spectra in perpendicular directions. You can see what one of these observing sequences might look like here in this GIF, where you have a direct image followed by 2 orthogonally dispersed images. With this mode, you can get low-resolution spectroscopy between 0.8 and 2.2 microns. You typically use this mode to detect high redshift emission line galaxies. The next mode is the SOS mode, which is the single object slitless spectroscopy mode. This also uses a grism, but it's the GR700XD grism, and it's typically used in those 2 subarrays which I highlighted before. With this mode, you can get medium resolution spectroscopy between 0.6 and 2.8 microns, and this is a time series observation or TSO mode. The way this works is that a single object is dispersed across its 3 orders, as you can see in the image here. And we typically use this mode to study time variable astrophysical phenomena, and its high spectrophotometric stability makes it great for studying transiting exoplanet systems. Next is the AMI, or aperture masking interferometry mode. Here you use a non-redundant mask, which is pictured here, to create an interferogram, pictured on the right. This is a contrast imaging mode, which provides high spatial resolution, moderate contrast imaging at the following wavelengths listed here, which correspond to the filters you can use with the non-redundant mask. And you can detect separations between objects between 70 and 400 milliarc seconds. This mode is great for detecting planetary and stellar companions, and possibly also for reconstructing high-resolution maps of extended objects, such as AGN. And lastly, we have NIRISS imaging. So this uses the full suite of our 12 filters, which goes from 0.8 to 5 microns. It covers the entire field of view. Right now, imaging is actually only enabled in parallel mode for cycle 1, but you can start using it in prime imaging in cycle 2. This is just a pretty picture of a dithered combined image, which actually spans a field of view that's a little larger than the detector. This was our focus field that we used during commissioning. Okay, so we've talked about the detector, and let's talk about some of the things that maybe are a little unexpected on the detector that we found during commissioning, and some things we knew to look out for. The first is our occulting spots. So this is something we've always known about, but which was more characterized during commissioning. The light from Webb's fine steering mirror is focused onto NIRISS's pick-off mirror, but the pick-off mirror is actually engraved with 4 coronagraphic occulters that are left over from the previous configuration of NIRISS, which was called TFI, or Tunable Filter Imager. And so when that instrument was respec'd to be what it is today, NIRISS, it was decided that there would no longer be a coronographic mode on NIRISS. However, the occulters are still engraved in the mirror and their effects are still present on our images. This means that for all external images, we actually see 4 occulting spots with diameters up to 31 pixels. The occulting spots are located about 11 arc seconds from the top of the detector. As you can see here, this image on the right is a full frame image of the detector, and the occulting spots are highlighted in this blue box and then zoomed in up here. There are 4, they range in size, as you can see here, and they get progressively larger. So what's the issue that you need to be aware of when you're looking at NIRISS data and analyzing your scientific images? Well, these occulting spots can potentially cover sources of interest, and I chose this image in particular to highlight that effect. This spot here could potentially be covering some interesting feature or clump in this galaxy. The good news is that you can mitigate these effects by using our medium and large dither patterns, where you can recover information over the 2 smallest spots, labeled 1 and 2 up here. But, however, there are still some small residuals left over for spots 3 and 4. Maybe using more dithers in your dither pattern, you could recover more information, or perhaps doing mosaicing. But if it's an issue, you can also avoid placing sources of interest near the pick-off mirror features. Okay. So we can't talk about Webb detectors without talking about 1/f noise, which, if you're familiar with Webb, you know about this already. All Webb detectors have this correlated noise called 1/f noise that is caused by the detector readout system itself. In general, this affects the near-infrared detectors more profoundly, but it can also affect MIRI, or mid-infrared detector. Okay, so as I was saying, the 1/f noise, most of the power is concentrated at low frequency, giving rise to the name 1/f noise. The problem is that this noise creates spatial correlations in the fast readout direction of the detectors, which for NIRISS is along columns. However, it should be noted that's along rows for NIRCam and NIRSpec. The issue as well is that this noise varies between the detector amplifiers and from frame to frame. So not only is it spatially variant, but also time variant. The problem here is that 1/f noise can have significant effects on low signal-to-noise data, and also there are other things to consider when you have spectral images, in particular when the noise is parallel to the dispersion direction. This can be a limiting factor in detecting spectral continua, and then when the noise is perpendicular to the dispersion direction, this can create fluctuations that you might mistake for emission lines. So how do you mitigate 1/f noise? If you remember before how I said only some of the detectors are light sensitive, well, the outer 4 rows and columns of near-infrared detectors on Webb are actually what we call reference pixels. These are pixels that are insensitive to light, but they do track drifts in the readout electronics. So the 1/f noise is corrected in detector 1, which is the first stage of the Webb pipeline, and the ref-pix step. What happens is the average reference pixel for each amplifier is subtracted from all applicable normal pixels in the same channel. However, even with the pipeline correction, there's still some 1/f noise that's not completely removed. You can see this effect below. So on the left here, this is a very jarring image because this is what happens when you actually do not perform the ref-pix correction in the pipeline. You see that the background noise is really quite different in each of the channels on the detector. And then there's also this vertical striping effect. That's that correlated noise that's along the fast readout direction. However, when you do perform the ref-pix correction step, you get an image that looks like this, and it looks a lot better. However, you can see there's still a lot of residual noise present in the spectrum. And so this is a pretty short exposure. It's less than a minute. And so the problem is very much exacerbated here with a low background. The vertical striping is still present, and we still see the channel dependence, particularly right here at this boundary between these two channels. You can see it goes from a low background to a higher background. So right now, we at STSCI are working hard to develop more robust methods of correcting this effect, and there are already some in development. Also wanted to pause for a moment to talk about how this can particularly affect time series observations for SOS. And those on the SOS team and outside of the Institute are working hard to develop a new 1/f noise correction for TSO images. The idea here is that for each integration, you create a median image and then subtract the median image from the original image to create a difference image. In this difference image, you use two local background regions on either side of the spectral trace to compute the average median value for each column. This you can refer to as the local 1/f noise. You take this local 1/f noise and then subtract it from each column in the original image. This is a figure provided to me by one of our NIRISS colleagues, Nestor Espinoza, which illustrates the effect. Here is the original image on top. Just below is a median 1/f noise as a function of column. And then below that is a difference image. So what you're seeing for the most part is the 1/f noise in the background, and then some part of the spectral trace. This is the first order, second order here. And then once you subtract that local 1/f noise, you get this corrected image below, which maybe at first glance doesn't look too different from the top original image. But the thing to take note of here is that that local 1/f noise, which was taken in these regions just outside the trace, has vastly improved the local 1/f noise at the spectral trace. So this right here is a lot more improved than this up here, but as you get further away from the trace, the 1/f noise isn't quite optimized. So it's very much a local correction which can improve your calibration of the spectrum itself. This method is being written up right now in some preliminary papers, so look forward to that in the literature soon. Okay, so let's look a little bit outside of the detector right now. You did hear from John about his NIRCam, wisps, and claws. This is very much related to that. It's the same light path that we're talking about. There's a stray light path called the rogue path, where light can bypass the primary and secondary mirrors and pass directly to the instrument pickoff mirrors. And so we knew about this effect, we knew to expect it, but there were still some interesting effects seen during commissioning, as you saw on NIRCam. For NIRISS, the rogue path susceptibility region is several degrees away in the V2, V3 axis. Again, very similar to what you saw with NIRCam. The scattered light from the susceptibility region causes a horizontal band across the detector at about Y of 575, and the height of that band is 25 to 30 pixels. We call this effect the lightsaber, which I love that name. So in general, the lightsaber is caused by diffuse zodiacal light that's in that susceptibility region, and the lightsaber is only about 1% brighter than the background. So maybe we call this the Padawan lightsaber. We just talked about what happens when the lightsaber is caused by zodiacal light, but we can actually run into more serious issues if there's a very bright star in that susceptibility region. In this case, the lightsaber can be up to 10% brighter than the background. And maybe this is the more evil Sith Lord lightsaber in this case. The lightsaber does affect both imaging and wide-field slitless modes, and unfortunately has increased spatial effects with the GR150R grism on wide-field slitless, and that's because that grism disperses along columns, and this is a horizontal effect, so it gets extended beyond its normal constraints. Okay, this is where I'm a little sad that there's no animations, because this was going to, the lightsaber was going to get turned on, but you can imagine that. In the meantime, I'm actually going to move this so you can see the effect that's underneath here, because this is an image of the lightsaber effect when there is a bright star in that susceptibility region. And so, you know, when we first saw this in commissioning, it was pretty surprising and alarming, but turns out, due to the great help with the Goddard ray tracing folks, we figured out pretty quickly what it was. The issue, in summary, is that when the lightsaber is caused by zodiacal light, that can affect your local background measurements in the region of the lightsaber itself. But when the lightsaber is caused by bright stars, not only can it affect the local and global background measurements, but it can also contaminate sources of interest that are in this region. How do you mitigate the effects of the lightsaber? Well, the easiest way is just to avoid placing bright stars in the susceptibility region. And right now, the NIRISS team at STSCI is actually performing these checks manually for all of our observing programs, but eventually there will be a tool available to the public where you can check if there's any contaminating sources in that region. We're also working to develop a lightsaber model, which can be subtracted from your images in the stage 2 background step. This is actually pretty similar to what John said they're doing with the NIRCam WISPs. So another thing we should talk about is when there is stray light from stars just outside the field of view. So light from sources just outside the field of view scatter off the detector baffle and onto the detector itself. So far, we've seen this happen with sources that are within about 200 pixels of the detector. The issue is that it's not always consistent. It can happen, it cannot happen. There seem to be some sweet spots around the detector where the effect is more pronounced. Typically, this is caused by bright stars. So far, we've seen it for stars that are less than about K magnitude 11. Preliminary investigation suggests that sometimes the total integrated flux of the stray light can be up to 60% of the source star flux. So it can be a significant effect sometimes. The affected area can be localized to the detector edge, or it can extend across the detector. We're still investigating the relationship between the stray light morphology and flux and the contaminating star's flux and position. So far, what we've seen is that the stray light can come in 2 different flavors. Dragon's breath, which was a term coined by our counterparts on HST, ACS, and WFC3, and then something I've been calling streaks or brushstrokes. So in the case of dragon's breath, this is a fairly well-known effect from HST, and we see it on web as well. So here are 2 instances of this effect. On the left is a pretty localized dragon's breath. This is this glow in the lower left corner here. It's actually being caused by the star whose diffraction spike you see here, and that star is a K magnitude 11.5. And then on the right, here's another thing we saw during commissioning. This is a much more extended dragon's breath effect being caused by this bright star here. Again, that's just off the detector, K magnitude 11. And this one extends to about halfway off the detector edge. Okay, I'm going to pause this GIF for a moment. Another thing that we see is these streaks and brushstrokes. So on the left here was one of the first instances of when we saw this. It was quite puzzling at first, and it actually took until we saw it a couple more times till we figured out what was going on here. So circled in that red is this streak here. This is a scattered light effect that's actually coming from a star over here. Again, you can see the diffraction spikes here from that star. That star is about K magnitude of 12. And the interesting part about this is that there's no connecting scattered light here. It's just, background, and then all of a sudden you get the streak there. That's an interesting effect. And sometimes this can get very pronounced if you have brighter stars. This is actually from an NIRISS program. And these are 2 back-to-back dither pattern positions, the offsets shown here. So you can see that moving, just a few pixels across the sky can dramatically change the effect of the scattered light. So in this case, we're getting a few different effects happening here. Here's a streak that's coming from this star right here. And then we're also seeing a little bit of dragon's breath from that star as well. The thing that's more interesting here is what's happening from this star. It's creating a small streak in one position, and then this very large diffuse feature that we're calling the brushstroke in another dither position. And so this is a pretty noticeable feature which you should be aware of as you're looking at your data, and don't be alarmed if you see something like this when there's bright stars outside the field of view. So the issue is that when a bright star is just outside the detector edge, you can get some scattered stray light on the detector. Sometimes this can be localized to the detector edge or extend across the detector, and sometimes it can contaminate faint sources. The other thing to be aware of is that for those streaks, which I just showed you, you should not be misconstruing those for some interesting astrophysical object, perhaps a nice edge-on galaxy. Nope, it's just a detector feature. You can mitigate the effects of stray light by avoiding placing bright stars near the detector edge. Because the effect is kind of unpredictable, if you're worried about this, you should take care to look around and see what's in the sky around your footprint. Okay, another thing that can happen from stars just outside the field of view is diffraction spikes. So this is something maybe a little unexpected, but when we thought back, it certainly makes sense. During commissioning, we obtained this image and were very surprised to see these bright bands crisscrossing across the detector. As it turns out, these are diffraction spikes from very bright stars outside the field of view. However, these stars are pretty far away from the detector. As you can see here, Tony Sohn, one of our NIRISS team members, did a really great investigation into this, went into APT, looked at the surrounding sky in Aladdin, and noticed that there were these two bright stars, I don't know, maybe 10 arc minutes away or so, and that their diffraction spikes, if you predicted where they would be on the detector, lined up perfectly with what we saw in the image. So this diffraction spike here next to the dotted blue line is actually coming from this star, and then the one next to the red line is actually coming from this star. In general, this isn't something you should be worried about unless it's important for you to have very low detector background, and you are nearby some extremely bright stars. So you could impose a position angle constraint for your observation to, roll the telescope in a way that this is no longer oriented on the detector itself. Okay, continuing along the vein of diffraction spikes, another thing we were definitely not expecting during commissioning was the discovery of something we've been calling anomalous diffraction spikes. This is something that we saw in the short wavelength filters, which for us is from F90 through F200W. There were these extra anomalous diffraction spikes, which we saw on bright stars. These spikes were determined to be caused by diamond-turning tool marks on the nearest off-axis mirrors. So these are like circular polishing features on the mirrors themselves. And because it's on the mirrors, it actually also affects FGS, which is in the same housing as NIRISS. Even though we weren't expecting it, because it's a part of the mirrors themselves, we went back and looked at some of our ground testing images and discovered that the spikes were actually present in those images. However, at the time, nobody seemed to notice or characterize it, and so this was something that we, quote-unquote, discovered during commissioning. The thing is that these anomalous spikes are pretty different than the normal diffraction spikes you see on typical web images. For one thing, they are much more diffuse, and their flux decreases with increasing wavelength. So in the filter F90, they're at their brightest, and one of these diffraction spikes contains about 70% of the flux of a normal diffraction. The other very interesting thing is that the orientation of the angles of the spikes changes as a function of source position on the detector. So it's a very strong function of the detector X position, and we see the extra spikes come in two different orientations, 11 and 5 o'clock, which you can see here on the left, and then 1 and 7 o'clock here on the right. And so as you step a source across the detector, the angle of these extra spikes will actually change, which was an interesting effect, but does make sense when you think about the fact that these are coming from circular polishing mirrors, circular polishing errors on the mirror. So the problem is not too, serious. It shouldn't have really any impact on your scientific analysis because the flux in these spikes is so low. However, the one thing to be aware of is that it could affect your PSF fitting. We've mostly seen this effect in bright saturated stars, However, it's very possible it could be seen in stars that are approaching that saturation limit. And in that case, it could affect your PSF fitting. So something to be aware of as you're doing empirical PSF fitting. Otherwise, it's not a serious effect. Okay, next is snowballs. So snowballs are really just a fancy name for a very big cosmic ray. Most cosmic rays affect just a few pixels, but snowballs can affect hundreds of pixels. Most snowballs are circular, which gives rise to their name, but some also are long streaks. They're thought to occur about every 20 seconds for a 2K by 2K near-infrared detector. We actually see them on mid-infrared detectors, but they have a different morphology, and because of that, they're called shower events. In theory, snowballs should be corrected for in the detector 1 pipeline jump step. However, it's been seen that this only addresses first-order effects of the snowballs and leaves behind some considerable residuals in some cases. So this is a very, exaggerated example because it's a long near-spec dark and we see the effect quite pronounced, but this should illustrate these residuals quite well. So here we have the image of a corrected snowball, and you see that it really doesn't look too corrected. In fact, it kind of looks like an eyeball. That's a little freaky. So I've tried to highlight the different regions on this residual and show you what's happening here. So in the middle, in this filled black circle, which is the same over here, that's actually where the snowball impacted and the pixels have been saturated and flagged as such in the pipeline. But just outside that region, there's this cyan circle. Those were pixels that were flagged as a jump, but they still had some charge spillover from that saturated region in subsequent groups, and because of that, those extra counts were not corrected for, and it results in a bright ring. Outside of that, we have this filled red torus. These are pixels that were flagged as a jump, but they had a below average count rate after the jump because some electrons were actually trapped in the pixels from the snowball event and then started to leak out. That's slow persistence. And then finally, this bright outer ring, or the magenta torus over here, those are pixels that had an increased charge rate due to the snowball itself, but not high enough to be corrected by the pipeline as a jump. And so we're getting this, residual bright ring on the outside. So as you can see, the pipeline is currently still missing a lot of, is still missing a lot of the effects from the snowball. And the issue is that snowballs are random, and because of that, they could contaminate any source of interest. There's not much that can be done from the user perspective about this, but at STSCI, we're working very hard to develop a new algorithm that will flag all pixels that are affected by snowballs. So stay tuned for that. This is a retroactive, correction that can be applied as well. Okay, last topic of interest are ghosts. So we're going to end on a spooky note. Ghosts are caused by internal reflections between the detector and the filters and the filter and pupil wheels. Only bright sources cause ghosts, and the flux of a ghost is typically about a few % of the source that's causing it. We see ghosts in both imaging and wide-field slitless observations, and it should be noted that when we're looking at dispersed ghosts, those are actually ghosts of dispersed spectra of imaging ghosts, not ghosts of dispersed spectra. That means that you get a ghost from the imaging mode and then gets dispersed, rather than every spectrum creating a ghost. Ghosts can come in many different morphologies, and they vary as a function of filter and source position on the detector. But the good news is that ghosts are predictable. A source will produce a ghost at the XY reflection point of what we call the ghost axis point, or gap. The gap varies with filter, and some filters actually have multiple gaps, and so a single source can create multiple ghosts. But not all sources produce ghosts. There's what we've been calling a ghosting zone. This is a sort of complicated function of distance and position compared to the gap, in which a source will actually create a ghost on the detector. So let's look at some examples. Here in the top row, I've collected a number of direct imaging ghost examples, and you can see the range in the morphology here. They can look anything like a PSF, which is, kind of alarming. This looks like it could be a kind of star, but there's something wrong with it. It's a little clumpy and it's not quite point source-like. They can also look just like little clumps of point sources themselves. For some filters, they always create multiple ghosts. So for F150, we always get a double ghost from a single source. And for F200, we always get a triple ghost from a single source. And interestingly, they can also look like these streak features for some filters as well. Things get a little weirder when we start looking at the spectral ghosts. So this is an image of F90 dispersed spectral image, which just happened to have a real source like perfectly aligned with a ghost in the column dimension. So what we're seeing here is the real source, 0th, 1st, 2nd, and 3rd order, and then just below that is a ghost, which is not coming from this source. It's coming from a source, way over here outside this image. And so you can see how different it looks from a real source. The 0th order is definitely a little clumpy, not quite point source-like. And then the 1st order, we get this like sort of strange clumpiness, which you may mistakenly confuse for emission lines or something like that. And then the 2nd order really starts to drop off, but we're still seeing some kind of like spatial dependence here with the clumpiness. And then the 3rd order is not quite visible here. We also see the same thing about double and triple ghosts in the dispersed images. So F200, which you saw up here, makes triple ghosts. Also does when you insert a grism. So here is a 0th order of 2 sources with the GR150C grism. You can see that there are actually 3 0th order spectra here. And then finally, there's also some very strange effects, which, for lack of a better term, I've been calling periodic blobs. We kind of see this interesting, like, binarity here, and then over here we see this, like, periodic, variation in the flux as a function in the dispersion dimension. So definitely something to be aware of. But like I said, ghosts are predictable. And so this is a great example of how you can predict and identify ghosts. This is from commissioning program 1063 in the F150 filter. Right here in the middle, this magenta X is the gap, that ghost axis point. And in the cyan circles are sources that are creating ghosts. And so their corresponding ghosts are in the small magenta circles. And I've drawn a line between the source and its ghost. You can see that every line intersects at this gap. And so that's how we determine and predict where the ghosts are. Another thing to note about this image is the, ghosting zone, the susceptibility region for ghosts. These stars marked with red X's actually should be producing ghosts on the detector, but they're not. And so it's just something you'll need to do as you ID the ghosts for every image, which can be done using software, which I'll talk about here. So the problem in general is that ghosts can contaminate sources of interest and also be misconstrued for astrophysical objects if you're not careful. You can mitigate the effects of ghosts by, again, predicting where they will occur and perhaps changing your observational parameters, like moving your source of interest away from where it previously was, or changing the position angle. But you can also recover information across the ghosts by using medium and large dither patterns. However, even with the large dither patterns, sometimes you may not completely clear the ghost footprint, in which case one of our former colleagues on the NIRISS team, Takahiro Morishita, developed this NIRISS Ghost ID tool. This is a additional software that's meant to be run between the stage 2 and stage 3 pipelines and can be used on both direct imaging and wide-field slitless data. What it does is identify ghosts using those gaps, which I mentioned before, and also the expected flux ratios of the ghosts. We know ghosts are, typically less than 5% of the source flux, And that's another way we can identify them. After the ghosts are identified, we flag all the affected pixels as do not use in their data quality arrays, and therefore they get excluded from subsequent calibration. Here I have an example of the effect. This is an image from one of our commissioning programs in which it was part of a 2-point medium dither pattern. This is just one of the dithers, and you can see this is a zoom in on a ghost. And then when you run the pipeline with default settings and create the I2D, which is, the final combined drizzled image, this is what you get. So you see now there's 2 ghosts because there were 2 observations in the dither pattern, and they're offset by the dither offset. The central regions of these ghosts have been, thrown away, and that's coming from the outlier detection step and the stage 3 pipeline. But there's still a lot of residual footprint from the ghost left over. And so if you stop the pipeline at stage 2, go and run the NIRISS ghost ID tool, and then jump back in and run stage 3, here's what you get. This is, again, default settings on the pipeline, and you can see that the footprint has been largely removed. However, there's still a little bit of residual structure here from where the ghost was originally. And it should be noted that you can do an even better job of removing the ghost footprint by optimizing the segmentation mapping parameters and the ghost ID tool. If you maybe extended the boundaries of the ghost, you could exclude even more of it in this footprint. And you can also improve your default pipeline results by optimizing the outlier detection parameters, which could help in a case like this, even when you don't use the NIRISS ghost ID tool. All right, so, we've talked a lot about, the things to look out for on the NIRISS detector and what you should be aware of during your calibration. Let's talk about, some good things. In general, NIRISS is exceeding expectations. So just like John said, things are working great on web. Everything's working as expected and sometimes even better than expected. So our imaging sensitivity is up to 25% higher than expected. Our wide field slitless throughput is up to 40% higher than expected. And for sauce, the throughput is better by 25% for order 1 and 50% for order 2. So we're getting a lot more bang for our buck. And I just wanted to include this really beautiful image and echo something that John said, that even when you're not looking for it, you will see so many galaxies with Webb. This was actually an observation where we were trying to observe zodiacal light for flats and ended up seeing this really beautiful galaxy interaction here, nice tidal waves. And just look at all the galaxies in the background. It's so much fun to just stop and stare at observations that weren't even meant to be deep fields. So Webb is working great. And just wanted to also highlight some of our other modes. I know it's easy to get stuck on imaging images, but we do have our lovely spectroscopy modes as well. And on the right here is a kind of a psychedelic image that one of our team members, Swara, made. And this is an RGB image where different filters from the same prism are assigned a different color. And so you can kind of see how a single object can get connected here from blue to red to green. And then on the left, this is the recent press release for WASP-39b, which included a NIRISS sauce spectrum, which is featured here. So just want to say thank you, and I hope you're all excited to use Webb and NIRCam and NIRISS for all your science.